in our standard model Lagrangian. The coupling I wrote like this, minus q prime bar h prime d prime r phi plus v over root of 2. This is the usual doublet. And there is another term which involves the presence of the Hermitian conjugate, charge conjugate doublet. Then there is one single term involving lepton fields. And the reason is that there is no analogous of dr in the lepton sector. There is no right-handed neutrino. Sorry, no analogous of ur. I have a prime also here. And let us concentrate for a moment on the term proportional to V, the term proportional to this constant shift in the Higgs field. And you may remember that V, with our choice of the Higgs hypercharge as only its second component as a doublet, so this is minus v over root of 2 times, this is coupled to the lowest component of the W, which is the left. The charge conjugation operator swaps the two components, so this is coupled to the first component of the doublet, u bar, prime, left, h prime, u bar right. And finally, this term is similar to this, so plus e bar left, h left, e bar right. Plus other terms which involve the coupling of couplings of the fermion fields with the Higgs field. Actually, in the unitary gauge, this would be exactly the same as this term I have already written down, with h of x at the place of v. As I said, these matrices in generation space, h prime up, down, and left, are arbitrary complex matrices. I would like to diagonalize them, because if I were able to diagonalize each of them, then this would be precisely a mass term for each massive fermion in the theory. And this can be done, actually. The point is the following. There is a theorem in linear algebra which is called singular value decomposition. And the theorem states that any complex matrix with no property, even non-square matrix, the theorem holds for rectangular matrix as well, can be factorized like this, like u dagger h v. For any complex matrix H prime, there exists two unitary matrices. such that H prime can be written as the product of U dagger H V, and H is diagonal. Diagonal with positive entries. It is not difficult to show. You have to figure out what the right eigenvalues and left eigenvalues of H are, and then you can show that this is true. And if you exploit this, you can diagonalize each of these three complex matrices by suitable choices of matrices U and V. U dagger D H D V D D prime R plus U bar prime left U dagger U Q V U U prime R okay. Plus Higgs couplings. And now HL, HU, and HD are diagonal and positive matrices. So now you realize why I chose to put a prime on the fields, because now I define new fermion fields like this. I can define D R equal V D prime R. This is a unitary rotation in the space of families, of quark families. And so on. And right equal V left E prime right, and E left equal U left E prime left. If I mix the fields in this way by unitary matrix V, D, U, D, and so on, what I get is a diagonal mass term for the fermion fields. Plus Higgs couplings. So once again, you see that we have circumvented the problem of the non-gauge invariance of of fermion mass terms by coupling bilinear terms of the fermion fields, not directly to a constant, but to the Higgs field, which transforms in a given way under the gauge symmetry. And this allows us to find out that a mass term for the massive fermions can be included in the Lagrangian. So the masses of the fermions are given by, see, for example, these now are diagonal matrices, so there is a term like minus hv over root of 2 psi bar psi for each of these for each of the fermions in the standard model, and the diagonal entries of these Yukawa couplings are related to the masses of the fermions through this relation here, so they have to be measured by measuring the mass of the different fermions. What we have to do now is to check what happens to the rest of the Lagrangian density when I perform this rotation. So far, so good. Here I have succeeded in introducing mass terms for the fermions, but now I have rotated the fermions among generations, and I have to check what happens to the rest of the Lagrangian. The fermion fields appear in the Lagrangian density, which involves fermions, which, if you remember, is the sum of three pieces. And it is immediate to check that this transformation here does not affect the free propagation term, because these V and U matrices are constant matrices. So if you have, for example, U bar left I D slash U left, and you rotate in generation space, in family space, all up left-handed quarks, nothing happens here because the derivative doesn't do anything on V. So this is equal to because is equal to 1. Because those are unitary matrices as a result of the singular decomposition value, and so on. For all the other term in the free propagation Lagrangian, there is no effect from that rotation. And the same is true for the neutral current term, because the neutral current term, because of what is usually called universality of couplings, all, for example, up left quark are coupled to the Z and to the photon in exactly the same way. So if you rotate them, once again, the unitarity of these matrices has no effect on this neutral current coupling Lagrangian. The only place where there is a measurable effect is the charge current interaction, and this is easy to check. For example, if I take the charge current interaction of up and down quarks with the W boson, which is written like this. This transforms into, okay, U prime. I have to invert this relation here, so I have U bar left, gamma mu, U there is a dagger for the inversion, but that there is another dagger because there is U bar here, so it's U and V D dagger D left plus emission conjugate. So the rotation that brings the mass term for fermions in diagonal form has an effect on the charge current interaction term, and the effect of this is this one. If you write the charge current interaction term in terms of mass eigenstates of fermion fields which have a definite value of the mass, then you end up with a matrix here which couples different generations. This is a unitary matrix. Sorry? UD dagger, thank you. This matrix I call V, and V dagger V dagger is U dagger U D dagger U D U U, which is 1. So it is a unitary matrix. But still, it is non-zero matrix. It must be measured. It is a fundamental parameter, which is a set of fundamental parameters, which arises from the Yukawa couplings in the original Yukawa Lagrangian. So this is an important point. In the standard model, there is an effect of flavor mixing, which is an effect of mixing between fields belonging to different fermion families, but it is confined in the charge current sector, which is precisely what we want, because flavor changing neutral current effects are very strongly suppressed in nature. And here we get it thanks to the Higgs mechanism. This is what is this matrix V is what is usually called the Cabibbo Kobayashi-Maskawa matrix. Nicola Cabibbo was the guy who realized that there is generation mixing at the level of the first and the second generation. Kobayashi and Maskawa extended this mechanism to the case of 3 different generations. And the reason why they did so is related to CP violation, which I will tell you about in a moment. There is only one last piece of information I have to give you. I have to check what happens with the charge current lepton interaction. And then we will say some detail about the Cabibbo-Kobayashi-Maskawa matrix. This is the charge current interaction with hadrons. The charge current interaction term with leptons is entirely analogous. And you see, here I have a rotation of left-handed lepton fields, but there is no need to rotate the left-handed neutrinos because there is no right-handed neutrinos. So I can, without any other effect, I can assume that left-handed neutrino are rotated exactly in the same way as left-handed charged leptons, because because this has no effect in any other term of the Lagrangian. And if I do so, this turns out to be exactly the same. So there is no generation mixing in the lepton sector in the standard model, as far as the neutrino are massless, of course. If neutrino are given masses, which is needed, as you know, then you will have a generation mixing effect also in the lepton sector. But this brings us out of the ordinary standard model because you need the introduction of right-handed neutrinos. Okay, so nothing seriously happens except the presence of the charge current generation mixing effect induced by the Kabib-Kobayashi-Mascava matrix. So we have added a bunch of new parameters in our theory. Before the introduction of the Yukawa term, we had very few parameters, essentially G, G prime, and lambda were the only parameters around, probably lambda and V. Were the only parameters which specify the standard model. Now we have more parameters. We have up quark masses with a generation index, so as many masses for up type quarks as there are quark generations, as many down quark masses, and as many charged lepton masses, the electron, the muon, the tau. No masses for the neutrinos. And then we have the parameters which are needed to specify the Kabib-Kobayashi-Mascava matrix. So it's useful to count them. And as far as we know, there is no constraint on the Kabib-Kobayashi-Mascava matrix except that it is a unitary matrix. So I have to count how many parameters, how many real constants are needed in order to specify a unitary n by n matrix. N is the number of generations. So a unitary n by n matrix can be written as the exponential of I, a Hermitian matrix, and I do that because it is easier to count the parameters in a Hermitian matrix. Hermitian matrix n by n has n real parameters on the main diagonal plus twice, this factor of 2 is due to the fact that the off-diagonal terms of a Hermitian matrix are complex numbers, and they are n minus 1 divided by 2. So I need n square real numbers to fix a Hermitian matrix, and this is the same number as the number of parameters which are needed to determine a unitary matrix. However, not all of these parameters are actually measurable. I can get rid of them, of some of them, by suitable field redefinitions, and I will show you. So, total number of parameters is n square. This number n square can be written as the sum of a number of angles plus a number of phases. What do I mean by that? If the Cabibbo-Kobayashi-Mascava matrix were a real matrix, if all the parameters in the Cabibbo-Kobayashi-Mascava matrix were real, then it would be an ordinary orthogonal matrix, and it would have as many parameters as the number of rotations in an n-dimensional space. So the number of angles, of rotation angles, is the number of coordinate planes in an n-dimensional space, which is n over 2. Right? You can couple two axes in an n-dimensional space in n over 2 ways, and this is the number of angles, which is 3 for n equal 3, which is the familiar result. So this is so the number of angles is 1/2 n square plus n. And the number of phases is just what is needed to fill the gap, the difference. Sorry? N minus 1. Sorry, n minus 1. N minus 1, so this is n minus 1 and n plus 1. Thank you. Now the point is that this number of phases here is not all of these phases are actually measurable objects, and the reason is that you can sorry. Just a second. Yeah. I can perform a redefinition of Quark fields. U left prime, sorry, U left, I transform U left into U left for each family. Is a U1 transformation, and the same I can do for the left down quarks. It has no effect in the whole Lagrangian. Again, alpha f and beta f are constants. They have no effect except in the charge current interaction term, and the effect on charge current interaction term is that of transforming V into V times E VFG, the FG entry of the Kabiboko-Bayashi-Mascava matrix is transformed into itself times the exponential of beta g minus alpha f. So I can remove some of the complex phases, some of the 1/2 n plus 1 complex phases in the Kabiboko-Bayashi-Mascava matrix by simply redefining the quark fields like this. And I can do this for 2n minus 1 entries. 2n minus 1 because there are 2n phases beta, 2n phases alpha, but the number of independent differences is 2n minus 1. So the real number of phases the true number of phases is not 1/2 n plus 1, but it is 1/2 n plus 1 minus 2n minus 1. Is n square plus n minus 4n plus 1 plus 2. This is interesting because this tells us that the Kabiboko-Bayashi-Mascava matrix can be, by suitable redefinitions of the fermion fields, can be cast into a real matrix for n equal 1 and n equal 2. For n equal 1 and n equal 2, there is no complex phase in the Kabiboko-Bayashi-Mascava matrix. The first non-trivial value, the first value of n for which there is at least one complex phase, is n equal 3. And for n equal 3, the number of true phases in the Kabiboko-Bayashi-Mascava matrix is 1. 3 minus 1 divided by 2 is 1, and this is 1. There is only one complex element of the Kabiboko-Bayashi-Mascava matrix. Why is this so interesting? The point is that if the Kabiboko-Bayashi-Mascava matrix is a complex matrix, then the CP symmetry is violated. This is easy to check. If you recall CP transformation properties of the fermion fields, then you will realize that you need complex Yukawa coupling, and this is the only place where you can plug complex phases in the couplings of the standard model, because the gauge coupling constants are real by definition. There cannot be any CP violation in the gauge couplings. So this is the only place where CP violation can be accommodated in the standard model, the Kabiboko-Bayashi-Mascava matrix. And this is possible only if you have at least 3 generations of quarks and leptons. Of course, you know that CP is actually violated. This is known since 1964. So well before the standard model was formulated, the first process where CP violation was observed is the mixing between K0 and K0 bar. And okay, so you can take the observation of CP violation and the result I have just shown to you to conclude that n equal 3 or more is a prediction of the standard model, in a sense. Phenomenology requires CP violation, but CP violation can only be there if there are more than 2 generations. So this is a prediction of the standard model which was confirmed by experiment. It is a very important point. So there are, for 3 generations, for n equal 3, there are 3 angles and one complex phase in the Kabib-Kobayashi-Mascava matrix, and there has been a considerable experimental effort in trying to measure these values. The present knowledge of these parameters is quite accurate, and but it took considerable effort. I will say something about this. This pattern of flavor mixing is one of the great successes of the standard model. It is not easy to achieve the same result in different contexts. For example, Technicolor. Technicolor is an alternative way of building non-zero masses for the W and Z bosons. And it works in that sector, but it is difficult to achieve in such a natural way the observed pattern of flavor mixing. There is a convenient way of parameterizing the Kabib-Kobayashi-Mascava matrix in the case of 3 quark generations. This parameterization is due to Lincoln-Wolfenstein, and it is written like this. Sorry, this lambda is not lambda which appeared in the Higgs potential, but traditional notation is lambda, so I apologize for this misuse of notation. The upper 2 by 2 square, upper left 2 by 2 square of the Kabib-Kobayashi-Mascava matrix is a rotation matrix in 2 dimensions. And if the angle is not too big, is not too large, you can expand to second order in the rotation angle to get this expression here. So you conclude that lambda is essentially the sign of the Kabib angle, which is actually quite small. Then you can check that the 3 entry of the, you can check, it is experimentally known that the 3 entry of the Kabib-Kobayashi-Mascava matrix is very close to 1. And in the Wolfenstein parameterization, this entry here is parameterized as a constant A times lambda square times a complex number, rho minus I eta. Then all other parameters are fixed by unitarity. A lambda square minus A lambda square A lambda square times 1 minus rho minus I eta. And the corrections to this parameterization are of order the 4th power of the sine of the Kabib angle, which is very small. So if you look at this parameterization, you realize that the diagonal entries of the Kabib-Kobayashi-Mascava matrix are dominant over the other entries, which means that generation mixing is there, but it is weak in a sense. It is of order lambda or less. The parameters 1, 3, and 3, 1 of the Kabib-Kobayashi-Mascava matrix are of order lambda square. And of course, this parameterization is achieved by requiring unitarity of the matrix V. You remember that unitarity is what guarantees that there is no flavor-changing neutral current around. Of course, you can test unitarity experimentally. And test of unitarity means that you have to define quantities psi, alpha, beta, index I, which is V I alpha V complex conjugate I beta. And unitarity means that the sum over I from 1 to n of psi I alpha beta is delta alpha beta. You can check unitarity by measuring the Kabibbo-Kobayashi-Mascava matrices. For example, this entry here, V UB, is particularly difficult to measure because it involves non-charmed decays of bottom mesons, which are quite rare, but this has been measured. You have to measure the entries of the Kabibbo-Kobayashi-Mascava matrix and to check whether they satisfy this relation here. And these relations here you can think of as, for example, for alpha different from beta, the off-diagonal entries of V dagger obviously have a 0 on the right-hand side here. So this relation can be expressed as triangles in some complex plane. The sum of three complex numbers must be 0, which means that they form a triangle which closes. And it turns out that out of the three of diagonal relations like this, there is only one which is non-degenerate. Two of them are triangles like this, which are difficult to distinguish. But one of them is actually far from the degenerate case, and it is usually the non-degenerate triangle is the one which is determined by these parameters rho and eta. So measurements of the Kabibbo-Kobayashi-Mascava entries are usually expressed in terms of measurement of rho and eta, and on the rho eta plane you can superimpose the constraints which come from measurements of flavor mixing processes, and you get a pattern. Of course, you have different constraints, different in shape in this picture. It is nice to see that there is only one small spot of intersections of these various constraints, which give you the correct values of rho and eta, which is a strong test of the correctness of the standard model in the flavor sector. I have a picture, but maybe I can show it tomorrow if we arrange for a projection. This is very interesting. It's very interesting and very peculiar of the standard model. There are many alternative proposals for the standard model, but none of them is so simple and elegant in describing flavor mixing. Okay, maybe I take a stop here. We reconvene in 10 minutes and we say something about the interesting point in flavor mixing in the standard model is that flavor changing neutral current are suppressed at tree level, but actually some flavor changing neutral current effects are measured. They are very, very much suppressed with respect to flavor conserving neutral currents. And this is natural in the standard model because they arise as loop effects. And there is a famous example which led to an estimate of the charm quark mass before the charm quark was observed. So I wanted to tell you about it because it is historically interesting. And the example refers to K0, K0 bar mixing. You know that K0 is has a quark model composition S d bar, and K0 bar is a bound state of an S bar and a D. So K0, K0 bar is actually a flavor changing neutral current effect. If you go to the standard model, you can achieve mixing between K0 and K0 bar by means of this diagram. Flavor mixing can only take place thanks to the exchange of a W boson. And in a vertex with a down quark and a W boson, you can emit an up-type quark, U, C, or T, which can then be converted into a down-type quark of a different flavor by means of another interaction. And you can check that this is the lowest order diagram in the standard model that provides you with an effective Lagrangian for the mixing between K0 and K0 bar. You can go ahead and compute this diagram. And what you get is an effective Lagrangian which induces processes with variation of 2 units of the strangeness quantum number. And the result is as follows. There is a constant, okay, I copy it from my notes, I hope it is correct. G Fermi square, MW square, divided by 64 pi square. Then you have a product of flavor changing neutral currents, S bar, gamma mu 1 minus 5, gamma 5, D, S bar, gamma mu 1 minus gamma 5, D. And then you have a coefficient which arises from the computation of this loop diagram. And this has a structure which is easy to guess. There is a sum over all possible up-type quarks running in this internal line, the upper internal line, a sum over J equal up charm top corresponding to the second internal fermion line. Then you have a combination of Kabibo-Kobayashi-Mascava matrix elements. For example, here you have a V, D, I, and here you have a V, S, I complex conjugate. So you have a product V, I, V, D, I, V, S, I complex conjugate, which is what I called psi I. Xi I, Xi J complex conjugate, and then you have a function which arises from the computation of the loop diagram, which is a finite diagram. And this function is a function of xi, xj, where xi is the ratio of the mass of the up-type quark I divided by mw squared. So this is the shape, the form of the effective Lagrangian for delta S equal 2, which is the relevant term in the standard model Lagrangian, which allows K0 and K0 bar to mix. And it is interesting to note that if all masses of the uptight quarks were equal, then this function could be factorized from this form, and the sum would be 0 by unitarity of the Kobayashi-Maskala matrix. So you have an extra suppression of the process, which comes from the differences between the masses of the various uptype quarks. So the point is that the mass difference between the two mass eigenstates in the K0, K0 bar system, K0 and K0 bar are not themselves mass eigenstates. The mixing matrix must be diagonalized, and the mass difference is proportional to the matrix element of these effective Lagrangians. Is twice the absolute value of M12, where M12 if you this factor of 1 over 2 mk arises because of the covariant normalization of states, and this minus sign arises because the Lagrangian is minus the Hamiltonian or something like that. And the mass difference between the two eigenvalue of the mass matrix is measured to a good accuracy. So you know this number, and you can relate it to the standard model parameters by means of this calculation. In order to do that, so what you get is something like delta M. I will give you notes about this. I'm being a bit sloppy here, but because it is a tedious calculation, but I just want to go to the crucial point without wasting time on details. What you get is delta M, the mass difference, which is a measured number, is equal to gf square mw square over 64 pi square mk, the mass of a cave mesons, the absolute value of sum over I and j of psi I, psi j, f xi, xj, times the matrix element K0 S bar gamma mu 1 minus gamma 5 d square K0 bar. So there are two difficulties here. One is computing this one, and one is computing this matrix element. This is actually not that difficult, because it turns out that the top quark contribution, when J is, or I is equal to the index corresponding to the top quark, then the value, the numerical value of the mass difference between the top quark and the up and charm quarks is not large enough to compensate for the strong suppression coming from the mixing between the third and the first and second generation. So you can forget about the top quark here. You can these sums goes from 1 to 3, from up, charm, and top, but you can forget about the top contributions. And the two remaining contributions can be computed in the approximation xi, xj much less than 1, because the mass of the up-type quark is essentially 0, and the mass of the charm quark is around 1.4 GeV. This is what we know now, but it was not known at the time, so it was just assumed that M charm was large but much less than the W mass. And if you make this assumption, what you get is that the function f for different xi and xj has a simple form. It is 4 xi xj divided by xi minus xj log xi over xj plus terms of order x squared, and the diagonal entries f xi xi are more or less equal to 4xi. So if you use this approximation here, if you trust me and neglect the top quark contributions in the sum, actually when John Ellis and Mary Kay Gaillard made this calculation, the top quark was not even, the top and the bottom quark were not around, so they didn't bother neglecting anything because there was no sign of the existence of the third generation. And what you get is delta M equal to gf square psi c square. Psi c is vc d vcs complex conjugate mc square times the matrix element. Now this matrix element here is difficult to compute, but it can be estimated. It is usually parametrized like this. It is usually written in terms of the k decay constant, which is measured times mk. This is what you would get if you were to insert the vacuum state between the two currents and take this as a good approximation. If you want to be complete, you put a parameter here which is usually called b, and b can be estimated, for example, on the lattice or by unitary symmetry arguments. B is of order 1. So you see that you end up with a relationship in which the only unknown quantity is the charm quark mass. Yes? Sorry? F square is the decay constant of the meson, of the K meson. The constant which is measured by measuring the decay width of the charged meson to mu nu. Is the analogous of the pion decay constant. So I was saying you end up with a relationship in which everything is known here because psi c is a function of the Cabibbo angle, delta m is measured, and so on. So you can invert this relation and get an estimate for the charm quark mass. And what you get is something which is quite close to the measured value, which was quite a success at the time. And the authors of these Lee and Gaillard. Now we are able to do this calculation in a much more refined way, in a much more accurate way, but this rough estimate is already quite good. So I will spend the rest of these lectures to tell you something, well, probably not all the rest, but part of the rest of these lectures to tell you something about the experimental confirmations of the Standard Model. Oh, I'm not completely sure about the dates, but you can check. Around 1964, as I said, the charm quark was observed, and more importantly, the weak neutral currents were observed, and I will say something about this. We had to wait until 1977 to discover the B quark, a family of hadrons which carry a new quantum number, which was called beauty or bottom, depending on the taste. The existence of the beauty family of hadrons is to be considered as a prediction of the Standard Model, as I said, because you need 3 generations in order to have CP violation, and CP violation was observed. So there must be a 3rd generation of quarks, and the 3rd generation of quarks was observed in 1977. In 1982, the W and the Z bosons were detected experimentally at CERN, at the UA1 and UA2 experiments. At that point, in the meantime, in 1988, the LEP machine started its operation, and this is important for many reasons. I will say something about that. But in 94, 95, the top quark were discovered. Top quark was discovered. The discovery of the top quark is extremely important because it completes the 3rd generation of quarks and leptons, but was largely expected at the time because LEP had shown that the B couplings of the coupling of the B quark to the Z boson were precisely those which are expected for a down type quark. So you need a partner of the 3rd generation B quark. And finally, in 2012, the Higgs boson was observed. Let me say something about weak neutral currents. I forgot my notes, unfortunately. Riccardo, may I go in my office and pick up my notes on charge neutral currents? I'll be right back. So the idea of the experiment which confirmed the existence of the weak neutral current is that you can perform a deep inelastic scattering experiment with neutrino beams. If only charged currents are there, then you expect to have charged lepton in the final state, which is what happens most of the time. And this is originated, this is given by W exchange of a neutrino beam with a nucleon target. But if you assume that there are also neutral currents around, then you also have a diagram like this, in which the exchanged vector boson with the nucleon is a Z boson. Here you have, as usual, a complicated hadronic state on which you integrate in deep inelastic scattering, inclusive deep inelastic scattering experiments. But here you have a neutrino instead of a charged leptons, or a charged lepton, which means that you measure nothing, essentially. You have to rely upon a measure reconstruction of the momentum of the hadronic system. And well, I have to say something about strong interactions, not much actually, but something we need. In the Parton model, the cross sections for processes with a hadron in the initial state, a real hadron, a nucleon, for example, in this case, are given by the Parton model expression, which is a sum over partons of a parton cross section where the initial state parton carries a fraction z of the original hadron. This is weighted by a parton distribution function, which I call fq, which is essentially the probability density of finding a parton with a fraction z of the longitudinal momentum of the hadron, and then you have to integrate over all possible values of the parton fraction. This is the Parton model formula. And these parton densities have the property that they cannot be computed by the theory. They are essentially non-perturbative quantities, but they are universal. They can be measured in a process and used in another process to predict the cross-section. So if you consider the neutrino cross-section induced by neutral current, the cross-section for this process here, and you take into account the fact that neutral current, you can take both a up quark or a d quark in the original hadron, then you end up with this expression. Fu and Fd are the parton densities of the up quark and the down quark in the proton, times sigma neutral current for the process nu up quark with an initial neutrino with an initial up quark with momentum Zp plus sigma neutral current nu d Zp. And then this quantity you can compute in the standard model. In the standard model, you can just compute this diagram. And they are functions of the coupling of the Z bosons to the up and down quark, which are in turn functions of the mixing angle between B and W3, the weak mixing angle. Then you can perform the same experiment with antineutrinos in the initial states. And what it turns out that the ratio R, which is the difference between nu bar neutral current minus nu neutral current divided by nu bar charge currents minus nu charge current. In this ratio, it turns out that most of the uncertainties, especially the dependence on the parton density, cancel out approximately. And this is a function of sine squared theta w only. Here, the UD entry of the Kabib-Kobayashi-Mascava matrix enters because in the case of charge current, the relevant diagrams is this one. You have a neutrino, a muon in the final state. And here you have a d quark and an up quark. So the vertex here carries a factor of V UD as a consequence of the Kabib-Kobayashi-Mascava matrix. Yes? Why are we averaging? You have to do some calculation. It's not... I skipped a few steps. I can give you the details in a moment. I think this is correct. We can discuss it later, maybe. I just copied the last step of a long... might be wrong, I'm not... but I think it is correct. I'm sure this is correct. Probably, yes. 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 That's maybe the reason why. If you carefully choose the nucleon target. Anyway, what the experiment Gargamel in 1964 observed was a non-zero value for this ratio. And the non-zero value for this ratio allows you to get a value for sine squared theta w. And it is important, the numerical value of this number. Sine squared theta w is around 0.23, something like that, which means that this angle is not too small and not too large, and G prime turn out to be of the same order of the proton charge. Which means in turn that the Standard Model is a good perturbative theory, as good as electrodynamic is. The coupling constant G square over 4 pi and G prime square over 4 pi are not much different from the fine structure constant. So perturbative calculations in the Standard Model are expected to be reliable, and in fact they are. It turns out that you have to make extremely precise experiments in order to see Standard Model radiative corrections. Let me check whether I find a quick answer to your question. No, I have to think it a little bit over, but I will. I mentioned LEP. LEP is an important point in our story. LEP was a E plus E minus machine, a collider of electrons and positrons, at an energy in the center of mass, which was in the first phase of LEP very close to the Z boson mass, close to the peak of production of the Z boson. This is LEP 1. While LEP 2 was pushed around year 2000 up to a center of mass energy larger than 200 GeV. And both phases have been very important in testing the Standard Model. In the first phase, the machine was operating at on the peak of the Z boson, so it produced an enormous number of Z bosons, which then decay, and you can study the decay of the Z boson in great statistical accuracy. In particular, what you can measure with great accuracy is the so-called forward-backward asymmetries for pair of fermions. The forward-backward asymmetry is defined like this. If you take the process E plus, E minus into a pair of fermion anti-fermion, a muon or a B quark or an up quark or whatever you like, you can define the forward-backward asymmetry as the the cross section for this process in the forward hemisphere minus the cross section in the backward hemisphere, which means that if you take the z-axis to be the beam axis, you can define a scattering angle for the outgoing fermion, and then you define the forward hemisphere as the one for which cosine theta is larger than 0, and the backward hemisphere the one for which cosine theta is less than 0, divided by the total cross-section. And this function here, this ratio, this forward-backward asymmetry, is a function, a computable function of the W angle, of the weak angle, because there is essentially only one diagram which dominates the computation, which is this one in which the Z boson is exchanged. Of course, you can exchange a gamma boson as well, a photon, but since the contribution is 1 over S minus mz squared for the Z exchange diagram and 1 over Z over S for the photon exchange diagram, if you are close to the mass of the Z boson in energy, then this contribution here is negligible with respect to this one. So you can compute this, and you can relate it to the weak mixing angle. Actually, this is at present the most precise way to measure the weak mixing angle, or if you prefer, to measure the two coupling constants G and G prime. And what you find out here is that you need to include at least one loop radiative corrections in this game in order to get the correct measured values for the forward-backward asymmetry. So you need the full machinery of renormalization and perturbation theory beyond leading order in order to test the standard model at the level of accuracy which is required by this machine. The order of magnitude is that they produce something like 10 to the 6 Z0 boson, so an enormous statistics for the 4 experiments that were operating on the lab machine. So this is the first of the important tests of the standard model. You can look at the lab cross-section working group, which is still working. They are still updating lab data analysis after so many years, and you can check at what level the standard model predictions are checked by this set of experiments. The second phase of LEP is also very important from our point of view, from the point of view of tests of the standard model, because at these large energies you can produce pairs of W bosons. The energy of the second phase of LEP is above the threshold of production of pairs of W bosons. And this means that you can test the presence, not only the presence, but also the size of trilinear gauge couplings. You have, for example, diagrams like this, which affect the calculation of the cross-section for E plus E minus into W plus W minus. And this is very important because the structure of couplings of trilinear and quadrilinear vector boson vertices in Young-Mills theory, in a gauge theory, is very special. All the couplings are related to the coupling of the vector bosons to fermions. They are not random coupling. They must take precise values in order for the theory to be gauge invariant. And the deviation of the cross section from the prediction of a gauge theory are very, very different if you take a generic vector boson theory. So this is a test of the correctness of the idea that vector bosons are gauge vector bosons. And again, this has been confirmed at a high level of accuracy, and this is a very important test. So the fact that if G is the coupling of fermions to gauge bosons, then G is also the coupling of trilinear vertices, and G square is the coupling of quadrilinear vertices. This is a very important point, very special of gauge theories. So this has been an interesting test. Of course, the main reason why the energy of LEP was pushed to these high values was the hope of producing a Higgs boson. A Higgs boson can be produced at LEP, for example, by means of this diagram. We have learned that coupling of the Higgs boson to various particles is always proportional to their mass, and the coupling to the Z is sizable. If you see that sorry, probably 215 is too much, because 100.5 plus 90 is 215. Yeah, they got very close to it, but they didn't manage. They didn't discover the Higgs boson at LEP. There was a big issue, of course, because the machine was running very well. After 12 years of operation, the detectors were known to great accuracy, and people at LEP wanted to keep running the machine for another couple of years, but at the same time the LHC was being built, and the management of CERN didn't want to slow down the progress of LHC, so they decided to stop. And it was correct, in fact, because it was very difficult. It would have been very difficult to discover the Higgs boson by means of the LEP machine. And also the other hope of LEP was to discover supersymmetry, of course. Already MZ was an enormous energy, center of mass energy at the time, and it was people were convinced that some new degrees of freedom would have appeared at such high energy as decay products of the Z boson with such a high statistics, but that again didn't happen. So anyway, the lesson from LEP is that we need radiative corrections. So we were right in searching for a theory which admits a perturbation theory beyond leading order, because you need that in order to describe data. And final confirmation of the fact that actually the weak and electromagnetic vector boson are gauge vector bosons. What else? I think that there are a couple of more important things I would like to tell you about the Yes, finito. So there are a couple of more important things, but I will tell you tomorrow. Okay. Okay.